Back. Today is the sixth video of our series of design a key value store, and today we will talk about the consistency models. Models, and if you didn't watch the previous four videos, I highly recommend them to you to watch them. If you watch them and you need just a quick review of what we have done, or like a quick recap, I'll do this in a bit right now. So basically in this series we are designing a key value store, and we talk about that whenever you have a system design interview and you have a question, all the time you will find that the question is pretty vague, and our duty as an interviewee is to just ask for clarification. So basically we will know exactly what are we designing, and from the question we will know the functional requirements and the non-functional requirements that give us a thoughts of how our system will look like, because we only have 45 minutes, so we will just focus on some specific part on a system. And we have this framework that help us to achieve this goal and into succeeding in the system design interview. First, it's the most important step is to understand the problem, and we understand the problem by asking clarifications questions, maybe from 5 to 10. After that, we propose a high-level design, and after that we get deep dive into specific aspect of our high-level design. After that, we wrap everything up. Maybe in the wrap up we talk about how to optimize or how to improve the performance of our application. So when we start in our first step is to understand the problem, we ask about like 5 or 6 questions, 5 questions, and no, four. There are 4 questions here. We ask about 4 or 5 questions, and you wanna ask from 5 to 10. Like, but I guess 10 is too much. Like from 5 to 7, I guess from 5 to 7 is pretty good. And from the questions, we know the functional requirements and the non-functional requirements, and it's pretty important that when we finish this step, the functional requirement, and we got the functional requirements and the non-functional requirements, it's really important to ask our interviewer, is is this enough? Is there anything that I am missing? Do you love that I should add something else? The thing like that, because the system design interview, it's about managing time and communication with your interviewer, and you should communicate with your interviewer and ask for clarifications in every single step. We don't want to assume anything. And basically we ask this question. I will not go through them. You can watch the video that we talk about the questions, the first video, I guess. And after that we have the functional requirements and non-functional requirements, and after that we talk about the proposed high-level design, and we talk about the cap theorem. What is the cap theorem? Yeah, the cap theorem. And we talk about that there is no system, there is no distributed system that can guarantee these 3 things in the same time. We all the time guarantee two specific things and just sacrificing the third one. So we have AB system, the availability and the partition tolerance, we're sacrificing the consistency, and we have a CP system, the consistency and the partition tolerance, while sacrificing the availability, and we have an AC system, which is the availability and the consistency while sacrificing the partition tolerance. And we said that the EC system is not a real world system, because the partition tolerance or the network faults are not something that we can avoid, so we have AP and CP only. And from our requirements, if we looked at them, that we are want a high availability more than consistency, so it's an AP system. And we said that because it's an AP system, we finished the proposal for high level design. After that we get deep dive into the system components, and we talked about the data partition, and we said that the data partition is basically we can't store all of our data into one single specific server, because our data are too much, and the other thing that we have a single point of failure. So we have a hash ring, and we just have multiple servers, and we store each key value into a specific server, or just we go clockwise. And by this way we are partitioning our data or sharding our data across multiple servers. And the other thing that we talked about is data replication, because we want to maximize the availability. So and to make sure that we just store our key our key value pairs in multiple servers going clockwise, and make sure that it's we are storing unique by server ID, because we don't want to work with multiple different nodes and discover in the end that these nodes only belong to one node, because all of them are in the virtual nodes. All of them are virtual nodes of a specific node, so we just make sure that it's unique by the server ID. And we talk about that we should create we replicate our data through multiple data centers to make sure that we have the maximum availability. And after that, we talked about the consistency problem, that when we have the data is we store our data into multiple replicas, or we will have a consistency problem. So one of the things that we would help us to have acceptance consistency, we have a quorum consensus. And quorum consensus, basically it's let's say that it's, you can think about the quorum consensus as like a quorum consistency. You can guarantee the consistency for us, and basically it just, you can think of the quorum consensus as a way that the server needs a confirmation for multiple for maybe like W or R for multiple nodes, and these multiple nodes are the quorum size to make sure that to accept a specific operation, or to consider this operation as a successful operation or not. And we talked about the quorum consensus, and we talked about we have the W, the R, the N, and the W is the right quorum. And for this example, the right quorum is 3. So when the client sends request to the coordinator, and you just could think about the coordinator as a proxy, the coordinator wait at least for 3 successful responses from the nodes to make sure to consider this request as successful. And we talked about if W plus R are bigger than N, it's a consistency. If R equals to 1 and W equals N, it's fast read. If W plus R less than N, the consistency is not guaranteed, but the latency is super low. And today we'll talk about something called a consistency models. So the consistency models is it's one of the most important aspects for when it comes to consistency. So when we talk about the consistency models, we have mainly 3 models. Sorry, there is a plane is out. Maybe the sound is so. Okay, the plane is gone. So when we talk about the consistency model, the consistency models basically defines the guarantees and the rules regarding how data is seen by different operations in our distributed system, in our distributed database. They specify the level of consistency that can be expected when multiple clients or processes are accessing and modifying shared data. The consistency models help us to ensure that data operations and their outcomes are correctly and predictably managed in the distributed system. And we have 3 main things. Let's just try to add them. Like number 1, we have a strong consistency. And the strong consistency is guarantees that every read operations in the distributed system, and every write also, returns the most recent write or an error. Just return the most recent, or just return an error. All nodes observe the same consistency view of the data. Any updates are immediately visible to all the subsequent read operations. Strong consistency often requires coordination and synchronization among nodes, which can introduce performance overhead, and it will our latency will be quite difficult. And we have what we called a weak consistency. and a weak consistency that it's a subsequence of read operations may not see most updated value because we don't have that strict rule. And we have last thing, I just weak consistency, consistency, and third, which is 1 minute, and third we have something called eventual consistency. And let's just type it. Eventual consistency. And let's just make this one bigger. Okay. And the eventual consistency allows for temporary inconsistency in a distributed system, but guarantees that given enough time and in the absence of further updates, all replicas will eventually converge to the same value. Read operation may return a stale or outdated data, but eventually all replicas will catch up. Eventually, eventual consistency is often achieved through techniques such as a synchronization, replication, and conflict resolution mechanism. And if we talked about that, because if we look at the strong consistency is usually achieved by forcing the replicas not to accept new read or writes request until every replica has agreed on the current write. And the problem that this approach is not ideal for high available systems because it could block new operations. So for example, DynamoDB and Cassandra, they are adopting the eventual consistency, which is I guess this will be the recommendation to go with the specific consistency model for our application right now. And if we want to talk about the consistency model, because I guess I will talk about what is the problem that comes from the consistency, the eventual consistency has a problem that the eventual consistency is often suitable actually for systems where immediate consistency is not required, and the focus on availability and scalability. And actually our focus in right now is in our availability and scalability. So we'll go with the eventual consistency and managing potential conflicts. We use it actually in distributed networks, databases like Cassandra, DynamoDB, things like that. The problem that comes, because we have challenges that comes with the eventual consistency, because sometimes we read a stale data or uneven data. So let's talk about what is the problem that we call the inconsistency that comes from it and how we can solve this inconsistency. Let's say that we have a client and let's say we have a server and we have a database. Let's call it D1, and let's just no. Let's just have this one and copy it again. Let's call I have server 1 and server 2 and D1 and D2. So let's say that we have in our database we have a property that called name, and this name equals to John. Okay, so these database we have this server is connected with this replica, and this server is connected with this replica, and both of them have John, the name of John. Oh, sorry. The name equals John. Okay, so the problem that come with the eventual consistency, the replications give high availability right now, but causes the inconsistency among the replicas. So if we how the consistency is caused actually. So if server 1 change the name and make it Jon Snow, okay, and and server 2 change the name have and call it Ali. Okay, and server 1 when it changed the name, and server 2 changed the name, and both of them they are changing the name like simultaneously. Right now we have a problem that we have conflicts, and we have right now the old value was John, and right now we have a new value for D1. D1 say that the name is not John anymore, the name is Jon Snow, and D2 say the name is not John anymore, the name is Ali. So we have conflicts, and how we can solve this conflict in the inconsistency, eventual inconsistency. The thing that we can solve this problem, that we use something called versioning, and we use something called a vector clock to solve this problem. And for the next episode we will talk about how we solve this problem with versioning and vector clock. And yeah, that's it for today's video, and hope you like my description. Today we went through a quick overview of what we are building, and we talk about the consistency models, and what is and what is suitable for us, and we choose the eventual inconsistency, and we talked about what is a problem that coming with the eventual inconsistency and how can we solve it. No, we didn't talk about how we can solve it. I guess next video we'll talk about how we can solve it. And I guess that's it for today's video. However, I just want to talk about if you like my content, make sure to subscribe, hit the notification bell, and give me a thumbs up so you'll never miss a video. And that's it for today's video, and see you in future problems.